in quantum mechanics recently, we've been studying rotational motion of two bodies moving together, and we've been studying the idea of spherical harmonics and how those fit into this whole story. I want to do an example related to that to illustrate some of the ideas that we've been looking at. In particular, I want to take an example that lets us ignore all of the pesky radial separation stuff in the two-body problem. What I'm going to look at instead is what's called a rigid rotator. The idea is we've got two objects, possibly different masses, whatever. Maybe it's maybe it's two atoms in some chemical molecule where they're a certain distance apart. Two massive objects that are a known distance apart, a very specific distance that we're going to say is not allowed to vary. So it's a very stiff, rigid rod, essentially, connecting these two objects. And what we want to know is what are the states of the system in general. We're going to try to understand that. In particular, I'm going to go ahead and say we know that the Hamiltonian of this system, inspired by classical physics, or derived from our two-body problem stuff, but inspired by classical physics, the Hamiltonian of the system, h hat, is the total angular momentum squared divided by 2I, divided by 2 times the moment of inertia of the system. And we could do all sorts of stuff to calculate the moment of inertia. That's not the interesting part. We're just going to use this as our starting point, as our Hamiltonian. So it's all rotational energy. This is just standard rotational kinetic energy in the quantum context. So what I want to look at is a specific case. We've got a specific case where we have a wave function of this particular rigid rotator that says the angular dependence of this thing. These are the things that specify it, right? We're specifying the angle between these two, the angle of the relative position. We know the distance is always the same, but which way does this relative position vector point from the first mass to the second mass? Which way does that point? Theta equals 0 in physics language, of course, is straight up toward the north pole of a sphere. Theta equals 90 degrees would be right on the equator. Theta equals 180 degrees. Pi radians would be straight down toward the south pole. So this theta and phi will specify the orientation. Obviously, phi is the angle around the the z-axis of our coordinate system. So if we want to say what is the radial dependence of this thing, well, I've got a scenario where somehow or other I know the radial wave function at time equals 0. Specifically, it's the square root of 15 over 4 pi times this bunch of trig functions, sine theta, cosine phi. That's our combination of, that's what we've got for our wave function. And what I want to know is, if that's time equals 0, what does this thing look like at some later time t? And what are the probabilities of getting different values of Lz? If we were to measure the z component of angular momentum of this object, what would be the probability of getting one value versus another value versus another? We want to know what those are. So that's our setup. We've got this wave function. What's this? I guess conceptually, this wave function is 0 at the North Pole, also 0 at the equator, also 0 at the South Pole. So 2 sine theta cosine theta is 2 sine theta, so you can think of this as a sine of 2 theta business. So it's likely to be, I guess, sort of at a 45-degree angle this way or at a 45-degree angle that way. Those are the most likely angles for this to be at. And cosine of phi tells me that it's most likely to be along the x direction or the negative x direction and those things. So I don't know, I'm almost imagining this as a couple of bulbs. I'll put it in green to match the place where that's written. I'm almost imagining the distribution of this as this is my z-axis and this is x and y is sort of into the board. I'm imagining something that's going to look almost like vroomf, 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 vroomf. Something kind of like that, where I've got, and not rotated particularly. This is dominantly along either plus x or minus x direction, not so much in the y direction, because that would give us cosine of pi over 2, which would be 0. So something like this that's most likely to be found at these 45-degree angles in the xz plane. That's our scenario. That's our setup. So okay, how do we answer these questions? Well, time dependence is all about the Hamiltonian. I know that if I want to calculate the time dependence of some state, we can use our standard results that psi of t is equal to e to the minus I h hat t over h bar times psi of 0. That's my time evolution equation for showing how a state evolves with time. So in this case, I know what h hat is. It's just the angular momentum operator squared. So we've got that, total angular momentum squared. And Yeah, so I've got this. What we need to do is figure out how to act with the Hamiltonian on our state. All right, this is the place where we say, gee, I don't know how to do that. Well, remember, right, this is just some wave function. It doesn't have energy stuff written into it. You could, if you really wanted to, take the L hat squared operator, take that operator and figure out how to write that in terms of derivatives and derivatives of theta and derivatives of phi, all sorts of partial derivatives, and do a big, no, we don't want to do that. If you can help it at all, what you need to do is find a basis for your state, a basis for your state where the Hamiltonian has some natural action. The position basis is something where we know how to do that. We could do this in the position basis. We don't want to. We want to find a better way to do it. In particular, the basis that we've talked about for these things is the basis of angular momentum eigenstates. And so we're going to choose, we want to write psi of 0 in the Lm basis, in the basis of angular momentum eigenstates. That's what we want to do. That's how we want to make progress on this thing. And to do that, again, the statement is we want to write our state as a sum over all of those possible angular momentum eigenstates. And so, I guess, technically speaking, I could say we want to write that psi of 0, psi of time equals 0, equals a sum from L equals 0 to infinity, and a sum from m equals minus L to L of coefficient CLm times the Lm state. That's what we want to do. If we had this form, if we had our state written in this form as some linear combination of the Lm eigenstates, then we'd be set because we know exactly how this works. We can use our very familiar angular momentum relations to figure out what the Hamiltonian does on each one of those. It's a great, easy problem at that point. How do we do this? We want to find these coefficients. Well, so standard thing to do, right? If you want to know that coefficient, I can say that the coefficient L comma m is going to be just that overlap of the Lm basis bra with our actual state, our psi at time equals 0. That's essentially the way that you calculate those coefficients. Great. And again, this is something where we need to figure out how to do this. The general way to do it, the most general case, if you don't have any shortcuts you can take, is to say, the way I like to think about it is inserting an identity operator. I want to write this as Lm with an identity operator in there, with psi of 0, where I'm going to expand that identity operator in the basis that I know how to deal with. In particular, I know my psi of 0. I know that in the position basis, the theta phi basis. So I want to put in an identity operator to let me use that. This is the most general case. We're going to take a shortcut. We're not going to do this, but I'll show you how to do it for the general case. We write this as that identity operator of Lm times my identity operator in the theta phi basis is an integral d omega of theta phi ket with theta phi bra and then psi of 0 stuck in there. Just so my identity operator is this part right here, the ket and the bra for my basis states, and summing over all those basis states. And of course, integral d capital omega, integral d omega is the angular integral, the integral over all theta and phi coordinates. I'll write it out in a second. The good news about this, the reason this is nice, the reason we can use this, is that we know what these pieces are. The Lm state here doesn't depend on our dummy variables theta and phi, so I can bring it right inside the integral. And this ends up being an integral of d omega of the Lm bra in the position basis times position basis form of my psi of 0, which is great because this is the part that I'm given in the problem. I can use that. So if I really want to do it, I know that this was given, and this is a spherical harmonic. And so if I really want to do it this way, I could work out each individual CLM coefficient. By writing this down, I'd be able to say that then CLM is equal to an integral d theta from 0 to pi integral d phi from 0 to 2 pi times the sine of theta, because that's part of my d omega. The measure for integration for angular things has that sine of theta in it, times, and then what's inside my integral, my integrand, ends up being, this is the complex conjugate of the spherical harmonic YLM, so this would be times YLM star of theta and phi, and I know I can find expressions for all of those, times my thing over there, my square root of 15 over 4 pi sine theta, cosine psi, and cosine phi rather. And that's an integral. I can find those. That is A, doable. I know how to do it. I know how to do these steps. B, hideous. Oh my gosh, that's ugly. This is an ugly integral for every single separate value of L and M. Maybe I can do it in general, but the spherical harmonics aren't exactly pretty functions. No, I want to find a shortcut. I've spent all this time telling you about what you would need to do. I want to look and see if I can find a shortcut, because I will tell you one of the defining characteristics of a physicist is that we're horribly lazy people, and we don't want to do things the hard way if we can help it. So I'm going to just stare at this function. I'm going to say, can I figure out anything about this particular function? Maybe I will luck out. I chose the problem. I'm going to luck out. Maybe I will luck out, and this function will be something that I can express simply without having to do a big integral like this. Well, let's think about it. When looking at this function, the wave function I was given in the beginning of the problem, I see that it has dependence on theta, but it's basically a trig function squared term in theta. And if I think about my spherical harmonics, hopefully you remember these at least a little bit from class. If I think about my spherical harmonics, I remember that each higher level in L, if I'm doing spherical harmonics LM, every higher level I go in L, I get one more power of a trig function as my leading contribution in that function. So L equals 0 had no angular dependence on theta. L equals 1 usually had either a sine or a cosine or something of theta, but not more than 1. L equals 2, the top term was a trig function squared. L equals 3, top term is cosine or sine of theta cubed, that sort of thing. I'm focusing just on the thetas right now. The phi's will come in a minute. But the thetas, it looks like, this looks for all the world like an L equals 2 case. Because I've got the sine and cosine but no more, I've got 2 powers of my sine or cosine of theta. So it looks like it's going to be an L equals 2 thing. If I'm lucky, it will turn out to be just that and not some weird combination of stuff. Looks like L equals 2, and then cosine. Well, cosine of phi in our standard physicists' language for these LM states, cosine isn't one of the pieces that naturally shows up there. What naturally shows up are e to the plus I m phi or e to the minus I m phi, those sorts of things where m is our thing. We know it's m, but cosine can be written in terms of those exponentials. I know that cosine of phi is equal to 1/2 e to the I phi plus e to the minus I phi. And so if cosine of phi is equal to that combination, this looks like m is going to equal plus or minus 1. Those seem to be the combinations I got, because this is one power of circulation around the thing, one phase factor, a phase factor of, order m equals 1 going around, and this is m equals minus 1 going the other way. So this looks a lot like I should be able to construct this out of those 2 spherical harmonics. And so indeed I can, and I'll write down for you what those 2 spherical harmonics are, just so we can see them. In particular, so L equals 2, m equals plus or minus 1. I can write down that YLM of theta and phi, but for LM, YLM for L equals 2 and m equals plus or minus 1, I can look this up. I don't want to calculate it from scratch because that's a pain if I can help it, but I can look it up. This is equal to minus or plus the square root of 15 over 8 pi times sine theta times cosine theta times e to the plus or minus I phi. Those are the pieces I need. These are exactly the functions that I want. The m equals the m equals plus or minus 1 spherical harmonics have that sine theta cosine theta term exactly matching what I want. So this is a good sign. This means, in fact, it's already becoming kind of apparent how this is going to have to work for this to match my original function. So let me write this down. And again, it's only dumb luck that I'm able to do this. It's only dumb luck that I don't have to go through the great big ugly set of integrals there. Well, dumb luck or the fact that I wrote the problem. But it's this thing. We've got this story. So okay, we want to put these together to create this. And it's almost a matter of just sort of staring and squinting at how this is going to do, how it's going to work. I need to get a sum of these two e to the I phi's. The rest of it will factor out if I combine the two. And that means I need them both to be positive. So I'll need to have y2 comma minus 1 minus y2 comma 1. If I subtract those, then that'll give me square root of 15 over 8 pi times sine theta times cosine theta times, and then if I subtract them, that gives me, if I do the negative 1, which is plus out front, minus the positive 1, which is minus out front, when I subtract, I'll end up getting e to the I phi plus e to the minus I phi, and so that term will turn into 2 times cosine of phi. And so if I bring a 2 out front, that gives me 15 over 2 pi, I guess. 15 over 2 pi because it goes inside the square root. Square root of 15 over 2 pi. I want square root of 15 over 4 pi. And so what I really want then is that my psi of 0, I better write it out in wave function form, in the position basis, theta phi, with my psi at time equals 0, this must equal 1 over the square root of 2 times y2 minus 1 minus y2 1. That's my wave function expansion in that way. My position basis wave function in theta and phi at time equals 0 is equal to this combination of spherical harmonics. Okay, why did I do all that? Why do I care? Because this combination of spherical harmonics is exactly what I get from specific states Lm, eigenstates Lm. That tells me in particular, I can just conclude directly from that psi of 0 is equal to 1 over square root of 2 times the 2 minus 1 state minus the 2 plus 1 state. That's my state. That's my time equals 0 state written in the basis of eigenstates of angular momentum, which is a basis that has a known, that are eigenstates of the Hamiltonian. That's good news. That means I'm actually, this is my basis that I need. This is exactly what I want. Because now, if I go and I do my time evolution, and I say e to the minus I h hat t over h bar applied to the time equals 0 state, well, if I look at that, I just need to replace h hat with whatever eigenvalue I get on each one of these two things. So usually I'd have to distribute this and have it act on each one of those two separately. But it turns out that h hat acting on state 2 comma m for any m is going to be 1 over 2i times the angular momentum operator acting on the state 2 comma m for any m. And since this is total angular momentum, it only cares about L. In particular, this equals 1 over 2i times L plus 1, I'm writing L, h bar squared times the original state, 2m. And of course my L is 2. 2 times 2 plus 1 divided by 2, this whole thing gives me 3 h bar squared over I times my original state of 2 comma m. 2 comma m. So the good news here is that my Hamiltonian acting on my original state, it just gives me a constant for either one of those. I can factor this constant out. This is my eigenvalue. I just plug it in where h hat is up there. Erase, erase, erase. I can plug that in, and I will find then that my wave function, lost an eraser. My wave function as a function of time, psi of t, is then equal to e to the minus I times this thing over h bar times t times 3 h bar t over moment of inertia times psi of 0. The only thing that changes here is that I get a time dependence. I get some state that is changing in time with a phase. It's an overall phase, but there's no relative phase between the two pieces. So this is actually a stationary state. This is a state that is an eigenfunction of the Hamiltonian. The entire state is an eigenfunction of the Hamiltonian because both have the same L, the same total angular momentum. So okay, I'm in this state. It's great. You could write this down as a function of time or something if you wanted to. We know the time dependence now. It's just a phase factor. We're set with that. The other question I asked was, what are the probabilities of getting different LZ values? Well, here again, we have a really easy thing. Our LZ is going to equal plus or minus 1. It's just our two M values. Plus or minus 1 are the only values of LZ we might possibly measure. So it's equal to plus or minus 1. And what are my probabilities? Well, I mean, this looks almost like basic problems in quantum mechanics now. The probabilities, each has probability 1 over square root of 2 squared. And just in case you're fuzzy on where that came from, so that's just 1/2. They're equally likely. In case you're at all fuzzy on where that came from, the idea is I'm taking, for example, the absolute square of, say, the 2-1 state with psi of 0, or psi of t, either way, taking that absolute square, and when I do that, the 2-1 state comes in, it's orthogonal to 2 minus 1, so the bra and the will cancel out, and this will be just the absolute square of negative 1 over square root of 2 times 2-1 with 2-1, that bra and ket. This is just 1 because it's a normalized state. We've normalized our eigenstates, and so it is just the absolute square of negative 1/2, or negative 1 over square root of 2, which gives us a half. So that's our whole story. There's a lot more that we could do with this, but this at least gives you a sense of how you do this type of calculation. If you have to, then go ahead and do the big ugly integrals over angles and find your coefficients, find all these, here my coefficients were 1 over square root of 2 and negative 1 over square root of 2, and zeros for all the other coefficients. If you have to, use the big ugly integral I talked about earlier. But if you can help it, it's always to your advantage to squint and see if you can just recognize how to write this in terms of spherical harmonics from the beginning. If you can, you're going to be set. You're going to be much better off. And that, I suppose, is the end of this little example. Hopefully that gives you at least a sense of how you can do spherical harmonic problems both the hard way and, much better, the easy way.